Hello, I'm Professor Rad, and this is Precalc video 231, Applications of Exponential and Logarithmic Functions, Population Growth. Now, in a previous video, we looked at something called a logistic growth model, where the constraints of the environment mean that the population is going to grow exponentially at first, but then sort of flatten out over time because of those restrictions. So in this video, we're going to be talking about a different kind of growth. This is called the Law of Uninhibited Growth, which means maybe you don't have any constraints for your environment. So the population is just going to continue to grow indefinitely. So for our formulas, we have our population growth formula, which says that P of t, this is function notation, it's not P times t, it's P of t, is equal to P naught or P sub 0 times e to the kt power. In this case, P of t is the population at time t. P naught is the initial population. Very often we have initial somethings having a subscript of 0, so that could be like your initial velocity, or in this case, an initial population. K is our growth rate, and T is our time. So let's take a moment and apply this formula in a few different ways, actually, to model this situation behind me. So what I'm going to ask you to do is pause the video and see if you can summarize just the information that's given in this top paragraph, and then we'll go through and we'll work through parts A, B, and C together. So pause the video and see if you can summarize the important information, applying, let me get out of the way here, applying the appropriate variables that we know. Okay, have you gone through it? I hope so. So let's work through it together. So as I read through this problem, we have the population of mosquitoes follows the law of uninhibited growth. That means we're going to be using this formula. In a lab, there are 1,000 mosquitoes on the first day. So that means our initial population is 1,000 mosquitoes. On the second day, there are 1,800. So what they're telling us here in this second sentence here is that when t is 1 day later, okay, so it's not 2, because we have a first day, that's day 0, and then the second day is day 1. So on the second day, there are 1,800 mosquitoes. So you can represent this by saying when time is 1, then or actually we could just say P of 1. That would be the best way to put it, I think. So P of 1 is going to equal 1,800. So the population at time 1 day later is 1,800. I like that idea. So that's it. That's what we know. So we don't know K, and we only know the population for a specific time. So for part A, they want us to find the mosquito growth rate. So we do know that when time is 1, so when we know the time is 1, we know the population at that time, and we know the initial population. So we know everything except for K, so we can use that to solve for K. So I'm going to set up my formula. P of t is P naught e to the kt. And then I'm going to substitute in 1. I'm going to write kind of an extra step. You don't necessarily need to write this one, but I'm going to say P of 1 is equal to P naught e to the t, or I'm sorry, e to the k, because t is 1. So we have k times 1, so we just get k. Now we can substitute in these values that we know. So P naught is 1,000 and P of 1 is 1,800. So 1,800 is equal to 1,000 e to the k. And now we just need to solve for k. So let's divide both sides by 1,000. That will give me 1.8 is equal to e to the k. And to solve this, we can simply just rewrite this in terms of logarithms. So we'll use the natural log and say log base e for the natural log of 1.8 equals k. Now, if they wanted us to approximate this, we could, but they didn't tell us to approximate it, so we're going to keep the exact value. So for part A, I'm going to write my answer over here. For part A, we found that k is the natural log of 1.8. And that's our exact value. We can just leave it like that. All right, so let's move on to part B, which says, let's write a function for the mosquito population. So when we go to write a function for the mosquito population, we want to make sure that we are keeping, like if this is our format, we're going to have P of T. That's like our Y in our formula. So we want to keep that. P naught, so we need to know our initial population. So that's a variable we have to substitute in for. E is just E, an irrational number. K is our growth rate, so we do need to know that to sub in. And T is our variable, that's time, and that's what's going to be changing. So just like when you have Y equals mx plus b, you need to keep the Y and the x in the formula. We need to keep P of T and T. So T is like the x, P of T is like the Y. So we'll sub in the values for P naught and for K. So we just found K. So we can answer part B pretty quickly here. So we're going to have P of T is equal to P naught, which is 1,000, e to the kt. So e to the natural log of 1.8 times t. So I'm going to write that as t times the natural log of 1.8. Now you can simplify this if you wish. In particular, we have e to the natural log of 1.8. So that's going to cancel each other out. But I'm just going to leave it like that for now, and I'll simplify it later if I need to. Let's move on to part C that says, when will the population be triple its initial amount? So we're going to work through this problem in a slightly different way than you may be wanting to go to instinctually. If you want to try this one out, actually, pause the video and try it out, and then you can compare it to the method we're going to use. And remember, there's always a method to my madness. All right, so for part C, as we mentioned, we want it to be, we want to know when the population will triple its initial amount. Now we happen to know in this case that the initial amount was 1,000, so triple that will be 3,000. So you could easily use 3,000 for P of T. However, in this case, I'm going to do it a little bit differently, because sometimes you're going to have an equation and you don't know the initial amount, and it turns out you don't actually have to know the initial amount as long as it's not 0. So in this case, I'm going to say we want P of T to be triple its initial amount. We want it to be 3 times that initial population. So let's go ahead and substitute into the formula, pretending like we don't know 1,000. So we have P of T is equal to P naught e to the kt. So we want P of T to be 3P naught. So we're going to put 3P naught on the left here. And this is going to equal P naught e to the kt. Then we can divide both sides by P naught. This is why we want the population to at least have something to start with, right? It can't be 0 because you can't divide by 0. So we'll divide by P naught to get 3 equals e to the kt. So notice if you're asked to find how long will it take for a population to triple or double or to be cut in half if it's a population that's dying out, you don't actually have to know what that initial population is in order to be able to solve for some information. Now, in this case, we do need more information to solve. We need to know what K is, but we found that out in part A. So we know that K is the natural log of 1.8, or we could have just substituted this whole thing into the formula we found in part B. That also would have been totally fine. So I'm going to put in for K this value we found. So we have 3 equals e to the natural log of 1.8 times t. And now it's up to you how you wish to solve this. I'm going to rewrite it using logarithms and proceed that way. So I'm going to write log base e, or natural log of 3 is this exponent. So I have the natural log of 3 is equal to t times the natural log of 1.8. And then we can find t by dividing by the natural log of 1.8. So we have the natural log of 3 over the natural log of 1.8 is equal to t. Now, again, they didn't tell us to round here, but let's kind of get an estimated value here. So we could, let's round it maybe to the nearest day, I suppose. So we're going to do the natural log of 3 over the natural log of 1.8. And that's going to give me about 1.869. so 1.869, is approximately equal to T. So what this means is this population of mosquitoes is going to be triple its initial amount before 2 days are up. I'm kind of suspicious of that. So I'm going to try 2. I'm going to substitute 2 into this formula and see if I get something bigger than 3,000. So let's just test that out. So 1,000 times E to the 2, so 2 days later, times the natural log of 1.8. And I typed in the wrong number. So let's go back and change that. I typed in 100 instead of 1,000. So that's, there we are. Yeah, and I get 3,240. So that's more than triple the initial amount. So pretty fast, eh? All right, so that's going to be it for this video on population growth. Now think back to our previous video where we talked about continuously compounded interest, and think about that formula and see how it compares to this formula here. So start thinking about that, and we're going to look at a third pretty similar formula in the next video. So in the next video, we're going to talk about half-life and carbon decay and radioactive dating. So looking forward to seeing you in that next video. In the meantime, I hope this was helpful for the law of uninhibited growth. And yeah, I'll see you in the next one. Bye for now.